Hi, today I'll be presenting my paper which combines deep Q networks and double Q learning to minimize car delay at traffic lights. The motivation for this paper is if you've ever been driving at night and you find yourself stuck at a traffic light and the light simply won't turn green when there are no cars in sight. That frustration is what motivated me to think about this paper and how can traffic lights be smarter and more intelligent and adapt to the surroundings. A lot of the work I've done has been influenced and has drawn heavily from the work done by Andrea Vidali, who also developed an intelligent adaptive traffic light policy, but using a single DeepQ net, whereas my work uses double Q learning as well as a DeepQ network and investigates some of the trade-offs associated with those. If your representation of the state space makes the problem intractable, then it will be hard for the agent to actually learn a policy in reasonable time. The state space representation that I'm using is drawn from the work done by Vidali, which essentially discretizes the roads approaching the traffic lights into grids, and these grids are of variable sizes. So closer to the traffic light you have more discretization, and so you're able to better capture how many cars are closer to the traffic light. The double Q learning algorithm essentially tries to address some of the issues with the Q-learning algorithm itself. The Q-learning algorithm is based on Bellman's optimality condition, which says that to solve a problem optimally, you simply have to solve the subproblems optimally. Q-learning, however, can suffer from some issues, particularly in the overestimation of the Q values associated with the states and actions, as well as a bias issue which can arise from training consecutive experiences. The double Q learning algorithm aims to tackle some of these issues by training two models at the same time, and so you end up avoiding sampling from the network that you're training to train the network that you're training. Deep Q networks essentially use a neural network to approximate and store the Q values associated with states, and so they take as inputs the current state and give as outputs the Q values associated with the actions that you can take given the states that you're in. The neural network architecture that I've used for this project is a 5 hidden layer network with ReLU activation functions besides the input and output layer, which are both linear. And the loss function I've used is a mean squared loss because I'd like to have the network output exactly the Q values. The results of my implementation are shown here. You can see that the double DQN performs better than the single DQN as well as the simple periodic baseline, and the double DQN actually outperforms the baseline model by 53%. Here you can see a video of the traffic lights which are implementing the policy as determined by the DQN agents. In conclusion, the double DQN performs well in the situations it's essentially trained for, which are the low and medium density situations. The performance is comparable and slightly better than the single DQN, however not by much. This makes perfect sense because the single DQN implementation already benefits from some of the other methods which are used to reduce bias and overestimation of the Q values. That concludes the presentation of my paper. Thank you so much for listening.